you any exercises. How did the other? But I presume the other Laura was gave exercises.
Yeah.
Well, okay. Well, I thought maybe we could do an experiment, and I could talk about something that I might refer to in my actual lecture. But in any case, it will be talked about by Simon in his lectures for sure. But I thought we could maybe do a quick and dirty canonical forms or positive geometries. Okay, and then Simon will do it all properly, but you can just sort of see what it looks like. And since it'll be so rough the way I do it, hopefully you can ask questions and then you can impress Simon. How does that sound? And then we can maybe do an example in real time, just so. I mean, but where you'll do it at least half or mostly. Okay, does that sound good? Or do you have questions about the other? I mean, I can do anything. I'm at the stage. Would you prefer to? Matteo, are you the boss? Who's the boss?
They can decide. You can ask by raising hand.
Okay, do people want to do a little crash course on canonical forms? Yes. Oh, this guy doesn't want to do it. Okay, fine. All right, that's fine. Okay, screw you. We're going to do it. So, okay, so since we're talking so much about some so there's some sort of geometric, there are some geometries, and these geometries sort of roughly live in kinematic space. But out of these geometries, we want to get some functions or forms, something we're going to call an amplitude or a wave function or something like that. And I want to talk about these relationship, these positive geometries and canonical forms. Now, again, I think this is Simone is really going to do this properly. But I just want to tell you the sort of I want to tell you the basic ideas so that you can see where the juice is very, very, very quickly. Okay, so let's just jump into some examples. Okay, so that so first, where does the word positive come in? The word positive at the most basic level is that if we want to define the interiors of interesting regions, the interior of interesting regions is always associated with some notion of positivity. So if we want to talk about the inside of a triangle, it's the convex hull of these 3 points, and that's a positive weighted sum of the 3 vertices. The positivity is important to be on the inside. So there's some notion of an interior that's associated with the positivity. Ultimately, we can think of it as a bunch of inequalities, a bunch of things greater than 0. Okay, so you always have to be on the same side of all of these linear equations. So whether it's the sort of convex hull definition or the linear inequality definition, there's some notion of positivity that tells us what the notion of an interior of a space is. Now, loosely speaking, positive geometries are just are geometric shapes that have boundaries of all codimension. That's the important thing. Okay, so the triangle is a positive geometry. It has codimension 1 boundaries, codimension 2 boundaries for the vertices. It has boundaries of all possible codimension. Whereas the circle, by this definition, is not a positive geometry because it has codimension 1 boundary and no points. Okay, so meanwhile, like this is a positive geometry. Okay. Again, it has boundaries of all possible codimension. And in many cases, there's a differential form called the canonical form that has the feature that it is determined. It's the unique, importantly unique form with logarithmic with d log singularities on and only on, that's the crucial thing, the boundaries, all the boundaries of the space. So that's what gives these things teeth, is that you give me you give me a geometry, but then there is some analytic object associated with it. There's this differential form that turns out to be unique up to overall scale and up to overall sign. There's an orientation associated with the whole thing. That's a unique form of logarithmic singularities on and only on the boundaries of the space. So again, there'll be whole lectures about this, but let's just jump quickly into the examples, just so you see why this is such a rich concept. It's a surprisingly rich concept. Just to say, any polytope is a positive geometry. So that's the kind of zeroth order interesting thing. If the space is a convex hall of a bunch of points or cut out by a bunch of inequalities, so it's a polytope, every polytope has a canonical form. There's even a concrete formula for the canonical form in terms of the volume of the dual of the polytope. So there's various concrete expressions for the canonical form. This expression is sort of implicit. It says, go out there and find the differential form that has logarithmic singularities on and only on the boundaries of the geometry. But in the case of polytopes, there's various super concrete formulas for it. But this notion of a positive geometry extends to cases where the boundaries are curvy, like this one, and even more interesting cases where they live in Grassmannians, so the boundaries are very, very curvy indeed. At least conjecturally, in some cases, it's been established that they are positive geometries, in the sense that these canonical forms are unique and exist. But in physics, we certainly believe in all the cases we've run into that they exist and they're unique, and so that's what we're talking about. But I'm going to not just talk about. I'm not going to even talk about general polytopes. I just want to illustrate some very, very simple examples, just so you get an idea what's interesting about them. So let's say the simplest case of an interval. So this is the x direction. Here's x equals a. Here's x equals b. So the first thing I want to do is write down what is a differential form that has logarithmic singularities on and only on the boundaries of this space. So what is my positive geometry? Is the interior of this interval. Sorry, I should have said that. Okay. So okay, let's try. So what do you think this form is? So I want to have a one form. It's going to be a top form. Okay? It's a top form in the space. So what do you think it is? It should have a logarithmic singularity near here. So what is the form that I can write down near x equals a? It's going to look like dx over x minus a. Okay, so that's clearly we're going to have a piece that looks like that. And here I'm going to have something that looks like dx over x minus b. Okay. And so what is your very first thought for what the answer is?
Add them.
Very good. Thank you. Victim number one. Okay. So all right. So let's just add them. Okay. So okay. Now this is almost right. Basically, there are two choices, and you picked the wrong one. This is almost right. But what's wrong with it? It's not right. Do you want to say what's wrong with it?
Yeah, it has a zero.
Doesn't have to do with having a zero. Both of them have zeros.
Yeah.
Sorry? Yes? Oh, were you just stretching, or did you have a thought? No. Yeah. Where else do they have singularities? So, good, yes. So what say it louder.
Singularities are not.
Where else are they? Okay, well, there's this thing has a singularity somewhere else. Yes. It has a singularity in infinity, exactly. Okay, so this has a residue at x equals infinity. Right? At infinity, it looks like 2 dx over x. So it also has a residue at infinity. So that's the restriction. It has to have the singularities on and only on the boundaries of the space. Okay, so the answer is this guy. Okay? And so, of course, I can simplify this to dx over x minus a, x minus b, plus minus a instead of b. Also fine, right? Okay, good. So that's our first example. Let's do the next example. Yes.
This unique up to sign, or you want to?
Oh, sorry. It's unique up to overall sign. Of course, so I have an overall sign, which means I should think of this as the whole space is oriented. So, there's an overall sign. Notice also that I'm assuming that the residues at the bottom on the points are 1 or minus 1. Okay, of course, I could multiply the whole thing by any overall factor, but by convention, we say that the residues on points are going to be 1 plus or minus 1. Okay. Okay, let's look at the next example. So this is a triangle, 0, 0, 1, 0, 0, 1. So this is y equals 0. This is x equals 0. This is 1 minus x minus y equals 0. Okay. Okay, so now I'm looking for a two form, right? I'm looking for a two form. And does someone want to guess what the two form is? Don't be shy. Take inspiration from this answer. Okay, I'll help. Dx dy. Yes.
1 over x plus 1 over y plus 1 over 1 minus x times.
You might multiply, right?
No, but if that's better than
But, you know, it's a famous Groucho Marx joke. You don't like your principles, I have other principles, right? All right, fine. Yes, 1 minus x minus 1. All right, very nice. Okay. Now, is this right? All right, but this is correct. But let's see what it means in action, though, because this shows what it means in action more. So because when it says it has residues on and only on the boundaries, it means much more than it just has poles at x and I mean these are obviously the poles, right? It should have a singularity on all the boundaries, but it means more. It means if I take, like, let's say a residue on the boundary where x equals 0, I should be left with the canonical form for this interval. Okay, that's the sort of recursive property that it has to have. Okay, so let's see if it's true. Let me take a residue in this, a residue around x goes to 0. Now, maybe Simone will define, I mean, we can define residue by taking little contour integrals. We can define it by an algebraic operation. You can define it. There's 100 ways of defining residue, but it's obvious what we mean here. We put x equals 0, and we get rid of dx. Okay, so after I take the residue of this form, I'm left with a 1 form. What is a 1 form that I'm left with? It's dy over y 1 minus y. Right? Well, that's very beautiful. That's exactly the canonical form of that interval that we just established a moment ago. With the minus sign and not the plus sign, right? So this thing goes like 1 over y squared at infinity. There's no pole at infinity, right? So all the poles are at y equals 0 and y equals 1. Okay? Obviously, the residue of y goes 0, goes the same way. Let's look at the residue at 1 minus x minus y equals 0. Let's say I solve for y, and I get dx over x, but y is equal to 1 minus x. Ta-da! There again, dx over x1 minus x is indeed the form on this line, where implicitly on this line we put y is equal to 1 minus x. Okay? All right, is that clear? Okay, so that's so this form has poles on and only on the boundaries of the triangle. In fact, for any simplex, this always works. If you have a simplex that's defined by a bunch of linear equations, L1 greater than 0, L2 greater than 0. These are all linear combinations of the variables in an n-dimensional space. Ln plus 1 greater than 0. So these Li are just some, I don't know, let's call them alpha ij xj. plus beta I. So there's some linear things in a bunch of variables. Then the canonical form is always dx1 through dxn over L1 through Ln plus 1. And upstairs there's the determinant. There's a determinant of this just this matrix. So each guy you write this matrix of beta I and alpha, the vector alpha I. Okay, we just take the matrix whose columns are all of those guys. That n plus 1 by n plus 1. Okay, so this is like beta 1, alpha vector 1, beta 2, alpha vector 2, beta n plus 1, alpha vector 2. Okay, and that's just there. When you compute, if you compute the residue on putting any n of these to 0, you get a Jacobian, which is exactly this determinant. It just cancels that. So the residues are all one or minus 1. Okay, so now let's do another example though. Let's stick in 2 dimensions. Yes. Yes.
Okay. So when we were talking about that example with the interval, you
Yes.
said that there was a pole and infinity,
Yes.
which means that we're thinking of that segment and living inside some.
Yes. Yes. When I drew this, I really mean this interior, the interior between A and B. Yes. So I want the form to have singularities only on these vertices and nowhere else.
Okay, and we're thinking of, you mean, when you say that only at those vertices, it means nowhere else on the projected line, right?
I mean, yes, I mean literally nowhere else on the projective line. Yes.
Okay, so are we thinking of this as living inside a projective?
It's very useful to think about it. In fact, I very much prefer living inside projective space. Yes, that's right. So when we talk about infinity, it's of course best to think about it in projective space. Yes, but I can say it all projectively. It's much more beautiful to say it projectively, but let me just say it like this. Yeah. Okay, so all right, let's do another example. Let's say you have a square or quadrilateral. Okay? And I'm going to just draw a generic one. So let's say this equation is some line L1. So it's some like AX plus A1X plus B1Y plus C1 bigger than 0, and so on. L2, L3, and L4. Okay. So every single time I draw this damn thing, I draw it so things are more parallel than I want them to. It's like my other problem earlier today. Sorry. Okay, so let's do it like that. Okay. L1, L2, L3, L4. All right. Okay, now what is the canonical form? Okay, now let me get us started. Because clearly you should have a singularity when all of these lines go to 0. Okay. Now, beforehand, that was the full answer, right? Up to some normalization upstairs. Can this be the full answer now? It's not the full answer, obviously. But, anyone want to complain about something? Go ahead.
I don't know for sure, but does it have something to do with where those two lines L2 and L4 intersect?
That's very good. It most certainly does. You care to keep going?
Yeah, so if you take the residue at the line L2, then this form of the line L2, then that will have 3 singularities.
100% correct. Exactly correct. So what we've just been told is that if I take the residue of this form on just let's say L2 equals 0, Well, I've set this to 0, but then along that line, L1, L3, or L4 could all be 0, right? So that means in principle, it could have a singularity here, could have a singularity here. It could also have a singularity there, right? And we don't want it to have a singularity on the star, right? Because we want it to be on and only on, okay? And of course, we have the analogous problem over here. Right? So there's sort of two bad points where the residue is not necessarily 0. Okay, so what do I have to do? Sorry? Including the numerator, what should I include in the numerator? Exactly, right? So I have to include this special line L in the numerator that's entirely determined by passing through those 2 points. Okay? So that's the canonical form of a quadrilateral. See, it's already kind of a cool object. It doesn't just know, I mean, this thing about having singularities on and only on the boundaries of the space forces a rather interesting numerator. I can't help but in every lecture that I've ever done like this, I've drawn the same picture and made the same joke, but it's actually true. It actually happened. So let's next do the pentagon. Okay, so I wanted the canonical form of a pentagon, and I have to draw it like this. Okay, where here is my actual pentagon. Okay. So here's, let's say, L1, L2, L3, L4, and L5. And now there are 5 bad points. So these are all things where things intersect, where the form should be shouldn't have any residue. So dx dy over L1 to L5. And when I was preparing some lectures on this subject, I was on a plane, I was drawing this picture, and the person seated next to me was obviously convinced I was a Satanist, and therefore drawing this over and over again. Okay, but now what do I have upstairs? Now this is really testing your classical geometry knowledge. If you were in the 1800s and you were in grade 10, you would know the answer to this question instantly. What is in the numerator now? Circle. Unfortunately, I drew it so it looks like a circle. Yes, but more generally, it's a conic, right? And that's what you would know if you're in grade 10 in 1850. Any 5 points uniquely determine a conic. Okay. There's a conic that passes through any 5 points, and that's the conic that occurs upstairs. Okay. So you see, this is the direct definition of canonical form, and already you see it's kind of a cool object, right? Okay. Now, this is in practice not how we compute canonical forms. Well, actually, maybe Simone will tell you how to compute canonical forms like this. There's a whole fascinating theory of what these points outside the polytope look like that's associated with the word that adjoint to the polytope. So there's a whole interesting world associated with these guys. So Simone will probably tell you something about that. But if you're not an adjointologist, the way you an easier way to compute canonical, or one way to compute canonical forms of polytopes is to triangulate them. So for example, let's go back to this case. I mean, I want to emphasize that it's not a volume, but the canonical forms have the same additive properties as volume does. Okay, so let's say I have this. If I want the canonical form for this 1, 2, 3, 4 object, well, I can get it as a canonical form of this triangle 1, 2, 4 plus the canonical form of the triangle 2, 3, 4. This guy plus that guy. And again, the orientation is important. Okay, so they're oriented the sort of obvious way. Now, why is that? You see, the crucial feature of the notion of canonical form is once you take a residue, you go to the boundary, and then the canonical form completely forgets about where it came from. It's entirely determined by what the boundary looks like and nothing else, right? So if I look at this guy, it has the correct residues here and there to look like, you know, it has singularities only on 1, 2, and 1, 4. But of course, it also has a non-zero residue on the line 2, 4. So does that guy. But the whole point is that the residue that they each have on 2, 4 are exactly the same. They're the canonical form of the interval 2, 4 with opposite orientations, and therefore they cancel when you sum them. Okay? It's not a volume, it's for sure not a volume, but it has the same additive properties as volume does. Okay, so you can so if you can triangulate a region, then you can get a nice formula for its canonical form. Okay. There is a final comment, and so a lot of the work goes into, you know, you have some nice geometry that's defined by some nice inequalities or some nice convex Hall condition or something, but you'd like to compute the canonical form. And so a lot is to just figure out how to triangulate it in some natural way. Okay, so if you find some natural ways to triangulate it, that'll give you natural formulas for the canonical form. Okay, finally, there's, yes.
You do that for the pentagon, then
Yes.
you must see that conic emerging in a funny way from double lines or something.
Yeah, I mean, it's not at all obvious. Yes, it is not at all obvious. Yeah, the fact that these two things are related is not obvious at all. I should say that again, in this formula, a formula like this has the feature that it has spurious poles that correspond to these internal parts of the triangulation. Those spurious poles cancel in the sum. Okay, so the formula that we wrote down to begin with is the completely correct. I mean, all the poles are obvious. But then you have to build this funky numerator that makes sure that that it's a D-log form that only has logarithmic singularities. Now, there's one nice class of polytopes where there's an especially simple way of writing down the canonical form. Okay, so that's just the last thing I'll talk about on general grounds here. Well, so yeah. So maybe I'll first say that different kinds of triangulation can make different things obvious. Okay? Maybe I'll just to say something else. For example, you can triangulate in such a way that you don't introduce any new vertices, but you introduce new lines. Okay, so if you do that, you're going to introduce spurious poles that cancel in the sum. You can also here's another way of triangulating this guy. I can get the canonical form of this as this big triangle minus this little triangle. Right? That's another way of doing the of triangulating it. And this one has the feature that it does not introduce any new lines, but it introduces new vertices. Right? So this does not introduce any new poles. But term by term, it has logarithmic singularities that are not there in the answer that cancel. Okay? And you can think of these two things as being very closely related to each other. They're related by thinking about triangulating not this guy, but the dual of this guy. Right? So a natural object, you can always take. Let's take this. But let me draw the dual of this guy. Okay, so if I draw the dual, all the lines are vertices. Okay, and all the edges are. So if I had, so if this is 4, 1, 1, 2, 3, 3, 4. Then this would be 1, 2, 3, 4, 1 in this picture. Okay. But let's say I took this picture and I want to triangulate this picture, let's say by plonking down the points in the middle and just making the sort of pizza slice like that. Okay. So that's a nice triangulation. That's a nice triangulation of this guy. What does this look like back in this picture? Okay. What this looks like back in this what this looks like back in this picture, actually, this is not precisely what I drew there is a special case of what I'm doing here. if we take this point and put it in some generic, if we take this point and put it on one of these corners, then it would correspond to what I'm doing here. But let me just draw it a little more generally first. So what you're doing is you're, this point on the inside here, the point on this side turns into a line on the outside. Okay. And so each one of these triangles is just the triangle that you would make going to any vertex here and just stretching it out, extending it out till it meets this reference line that you add. Okay. So there's this line, there's this triangle, there's, I don't know, from this guy, there's this triangle, and from this guy, there's this triangle. Okay. And so once again, what I've done is add this reference line. Every point I have extended the point out to make a triangle that is formed by the two lines that meet at the point together with this line of infinity. And then you can see that this guy that we started with is this big triangle minus this one, minus that one, plus that. Okay. So there's always this inclusion-exclusion type formula that corresponds to, in the dual, just triangulating with a point on the inside. In the original polytope, you just put, in this case, it was two-dimensional. If we did it for general dimensionality, we just put some plane at infinity. Okay. And now this strategy always works to give you a bunch of simplices when the polytope is so-called simple. Okay. If the polytope is such that at every vertex you have, if it's a d-dimensional polytope, but if at every vertex you have exactly d faces meeting, then this trick is always going to give you the sum of a bunch of simplices, right? Because at every vertex you just extend out and you get a simplex made out of those d guys meeting at the point together with this plane at infinity. Okay. So this is this amusing inclusion-exclusion sort of triangulation always gives you a formula for the canonical form of any simple polytope. And the formula is very simple. You go to every vertex of the polytope and you just multiply the product of all the linear factors that meet at that vertex together with that dumb determinant that normalizes it that we just saw for any simplex. And you just sum that over all the vertices. And that's it. So that's a formula for the canonical form of any simple polytope that can be understood as a triangulation of the dual polytope with a sort of point in the interior in this obvious way. Again, it works in the dual because in the dual the polytope would be so-called simplicial, so that all of its faces look like simplices, and that's why if you put a point in the middle and then just send rays out, you'll also get a sum of a bunch of simplices in exactly the same way. Okay, and I'll leave it as a little exercise to see how this picture is actually exactly this picture when you take this point and you move it to one of the corners. All right, so that. Okay. Now just remember that because, and now I'll make the general comment. So something that we found is that there's sort of one geometry that describes the amplitudes, for example. It could be the Associahedron or the amplituhedron or whatever. But you learn many, many different natural ways of triangulating it. Different ways of triangulating it make different features of the answer manifest. Sometimes some of the ways of triangulating it look like Feynman diagrams. Okay? In the simplest story of the Associahedron, we'll talk about in a moment, one of the triangulations is literally Feynman diagrams. Okay? But there's many other triangulations that are not. And you can also see that this thing with the Feynman diagrams is doing something very artificial. Every single term has a singularity at infinity, which is absent in the actual answer. Okay? So that's a very early indication that when there's a geometry that's associated with your observable, the diagrams are always missing a symmetry, right? There's a singularity here. There's some bad behavior in infinity that every diagram has term by term that only cancels in the full sum. If you're a mathematician, maybe this doesn't excite you so much. If you're a physicist, and you've spent 20 years talking about Wilsonian naturalness, this should shock you. This never happens. This is not supposed to happen in field theory, that there are zeros, things that we don't understand from any standard symmetries. but they happen everywhere. It's not just like a random happenstance here or there. It's a ubiquitous phenomenon, it turns out, that there's behavior at infinity that's much better for the full amplitude that you can't see from each diagram alone, right? And if you're a particle physicist of a certain generation, this should make your spidey senses tingle, that this should be useful for something, because this is exactly what we're stuck with in trying to make sense of some of the major mysteries from the particles. Anyway, that's a side comment for maybe two people. Sonia, there you go. one person in the audience. We can cry afterwards together. You know. All right. Okay. So, okay. Okay. Any questions about this? All right. So again, you'll see this. You'll see this much more nicely in Simone's lectures. Okay, maybe I'll make a final comment. Something that people sometimes ask me in lectures like this, and it's an unfortunate feature of finite time, is that, okay, so apples, this n equals 4 super equals 5 cubed, blah, blah, there are these geometries, and every single thing looks like it's just pulled out of the blue. Like what, why would you think about these things? You know, what would make you think about anything like this? Like, how do you actually do it? How do you go find these geometries? It is super easy how to find these geometries. So let me tell you what you do. I'm not guaranteeing it'll work, but I'll tell you what we've done, okay? And it's just this. Every time you run into some object, every time you run into some interesting object, especially if that object, the observable, gives you something that looks like rational functions, pay very close attention to the residues of that rational function, okay? So if you have an interesting rational function that comes out of some physical calculation, the moment it's rational, you should be like ding, 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 and then go and compute its residues obsessively, okay? If you find that all the residues of this guy are plus or minus 1, there is a very good chance that there's a geometry associated to it. It's not guaranteed. It's not guaranteed that every D-log form is the canonical form of some geometry. But it's such a non-trivial thing to happen that when it happens, you should be very, very excited, and something likely is going on. Okay, let me just give you a small example. Let's talk about our cosmological example. And actually, let me make things a little bit. So I'm going to just look at the single diagram for the moment. If you remember, we're supposed to draw these tubes, but the dependence on this K1 and K2 is always in the sum, K1 plus K2, right? Because no matter how it enters, they're always going to occur together, right? So that motivates me to draw a little truncated version of this picture. And I'm going to associate, instead of calling them Ks, I'm just going to call the sum of all the Ks that enter this vertex, I'm going to call it X. So there's an X1 here, and an X2 here, and the K of this intermediate guy I'm going to call Y. All right, so in this case, my answer was 1 over X1 plus X2, X1 plus Y, X2 plus Y. Okay? And now already there's something a little bit interesting here. So by the way, another thing that you should be on the lookout for is that when you run into physical observables and their functions, turn them into forms whenever you can. Okay, because the residues of functions don't mean anything. Residues of forms mean something. Okay, so I have to talk about forms. But you know, you're a physicist, so don't try too hard. If you're a physicist, your mathematician tries hard as you want. Okay, so but here, how would I turn this into a form? Well, I mean, I'm going to turn it into a form by making it dx1, dx2, dy. That's very pleasant. That having turned it into a form, this is now homogeneous, right? Okay, so that's another general lesson. The moment anything is homogeneous, imagine projectivizing it, right? If it's not homogeneous, don't. But here it makes sense to projectivize, right? So I'm going to imagine this whole thing is actually mod GL1. Okay. Okay, so for example, I'm going to use that GL1 to set y to 1. I can certainly do that. Okay, if I set y to 1, then this turns into dx1, dx2 over x1 plus x2, x1 plus 1, x2 plus 1. And ta-da, that's a D-log form. That's a canonical form of a triangle. The residues are plus or minus 1. Okay? Of course, it doesn't matter who you projectivize, so it's a D-log form. Okay, that's not super exciting, but this is now an honest exercise for you. Do this for the next case. So let's say we have this diagram. Okay, so again, I'm going to simplify this to draw it like this. So I'm going to call these variables the sum of the energies here, x1, x2, and x3. This is some y1 and some y2. And remember, we have these two tubings plus the other one, but this one in this language is 1 over x1 plus y1, x1 plus x2 plus y2, x2 plus y1 plus y2, x3 plus y2, and 1 over x1 plus x2 plus x2. There's this one plus flipping 1 and 3, and x1 and x3, and y1 and y2, plus the other guy. Okay. And now this is the exercise for you. Take this guy again. I'm going to once again nicely it happens that if I multiply by dx1, dx2, dx3, dy1, and dy2, it has it's homogeneous. Once again, I can projectivize, so I mod by GL1. And now the exercise for you is to compute the residues of this guy. So just put it on Mathematica. Okay? Just put it on Mathematica, take residue. And what you should find is that the sum of them does something wonderful. Okay? Okay. So this is a more non-trivial example because the sum actually matters. All right, and that's actually what we actually did. So, you know, when we were playing around with these cosmological wave functions, you see the rational functions, the weights are correct. That's exciting. But then you just do these experiments to see whether there's a chance that you're dealing with a D-log. Right? Yes.
If you like plug into Mathematica and do residue, like as I know, like when you do residue with like multivariable
Yes.
functions, you have to do it like along some direction.
Oh, you know, one at a time. Yeah, that's right. Yeah, so you take residue, so you just stare at your poles, you pick one of the variables, you pick one of the poles, and you just take the residue around there. Then just, of course, if you're smart, you write something that checks all of them at the same time. If you're me, you just do 10 of them until you're convinced it's correct. So yeah, that's right. You just do it successively, and then see that at the bottom you get plus or minus 1.
For all like
All possible ways. That's right, and that's a nice thing. I mean, that's the point. You just it's just there's nothing to do. You look at the expression, you pick any pole and any variable, and you solve for the variable. Any pole and the variables, you get something, and they just keep going. That's again, it's not guaranteed. It's not guaranteed that this gives you a canonical form. For example, bad things can happen. Like let's say you have two shapes that have nothing to do with each other. Here's a shape over here and a shape over there. If you add their canonical forms, you'll get a D-log form. Still, but it's not the form of one object. It's the form of the sum of two of them. Okay, so bad things can happen. They sometimes do happen, but they normally don't happen. Okay, so if this business of unit residues happens to you, something magical is happening regardless. Okay? It's so non-trivial to get something with unit residues that it very likely has some kind of geometric interpretation. And this has happened like 4 or 5 or 6 times. I mean, so that's one window in to discovering these kind of objects. All right, okay. I think that's it. Matteo, should we take another? Do you want another small break?
No, there is no small break.
There's no small break. Okay. Very good.
To finish when we advertised 45 minutes left.
Sorry?
To finish when we originally advertised about 45 minutes.
45 minutes left. Okay. It's gonna be tricky. All right. Okay, so now we're going to finally talk about Associahedra and Cosmohedra. Okay. Okay, so if we talk about first the amplitudes for trace phi cube theory, then our claim is that the amplitude for trace phi cubed is the canonical form up to some factors that is essentially the canonical form of an associahedron that lives in this in the kinematical space. So I'll define what this is in a second. But first, let me just talk about but first let me talk about just combinatorially what is the associahedron. So and also how an experimentalist particle physicist would discover it. Okay, so the story I like to tell is that imagine that you're an experimentalist who's measuring these, who lives in this world with these scalar particles, right? And they are, and you have your finger on the dial of the momenta of all the particles. Okay, so in particular, you can adjust all the xij. Okay, you can adjust all the xij. And well, so what do? You turn the dials, you see what happens. But what are you probably most excited about? What you're most excited about is that when you set the xij's to some values, the amplitude blows up, right? Of course, if we write the amplitude in terms of the x's, it's when the x's go to 0. If you do it in terms of the pi dot pj's, it's in some funny spot. But anyway, if you write them in terms of the x's, it's when the x's go to 0. And so that's the first thing that you notice. You notice that there's poles when the xij's when the xij goes to 0. And then what you do with this observation in this imaginary world depends very much on the kind of experimentalist you are. There are some experimentalists who are sort of closet theorists. So they like very much. They're like, oh, there's a pole. I know I should look at a residue. I know about Cauchy's theorem, so I should look at a residue. So this closet theorist experimentalist goes and makes very precise measurements in the neighborhood of x goes to 0, and they discover that the amplitude factorizes. Right? That's the amazing thing that they discovered. Factorizes into product of lower pieces. And then they go to the conference in this imaginary world and they say, there's something crazy going on with these particles. But when I put these x's, these special values, they factorize into lower things. And there's a theorist in the audience named Feynman. He says, oh, I know what's going on. It's some of Feynman diagrams that I just named after me, right? And that explains it, right? That explains the pattern that they see. Okay, so that's one thing. If factorization is the star and the only thing you know about, then you're led to this picture of Feynman diagrams. But there's a different kind of experimentalist who is the hero in my story, and every time I've told this story, who hates theorists, okay? And the really great experimentalists really hate theorists. And they don't give a rat's ass about Cauchy's theorem, but they're excited about something else. They definitely like things blowing up, okay? But there's very natural to ask a question, if something blows up, can I make it blow up more, right? And that's another question. So that's a question of, what is the pattern of x's that I can put to 0 that makes the amplitude blow up? Okay, so for example, there's something interesting that if you set at 4 points x13 to 0, nothing will blow up ever again. Even if I put x24 to 0, then I'm done. You know, it doesn't blow up anymore. That's because the amplitude does not have simultaneous poles when x13 and x24 both go to 0. They're crossing chords. We can't see them together. That's space-time locality, all that stuff we're talking about. But it means there's a pattern in how the poles can come together. Okay, I can have x13 or x24, but not both of them. Things get much more interesting at 5 points, right? Because at 5 points, they would discover, well, what are the pattern of x's that can come together? They're not any two random x's. Okay, there are some set of x's that can come together. So this hero experimentalist says, okay, let's just make a list of the guys that can come together. So, for example, for n equals 5, x13 and x14 can come together, and that'll make the amplitude blow up twice, right? Again, cheating, looking at either finery diagrams or the triangulation, that's because there's a triangulation that has 1, 3 and 1, 4 in it. Okay? Okay, so that means that if I set x13 and x14 to 0, I'll get it to blow up twice. But they don't know about this picture. They just observe this fact that it's when x13 and x14 goes to 0, and it's sacred thread to x14 and x24. And meanwhile, just single blow up is just x13, x14, x24, and so on. So there's single blow-ups, double blow-ups, that's it in this case. And then all these pairs, I won't keep by writing them. But like any good experimentalist, they don't like just presenting their data as this crappy looking list. They try to make it look nice. They try to present it as a picture. And there is a beautiful picture that captures this whole pattern of singularities. Okay? It's slightly non-trivial. In this case, it's completely coincidental, but it looks like a pentagon again. Okay? But there is a picture, and this is coincidentally a pentagon again, but where the edges of this pentagon correspond to the single pole. So I can have a pole where x14 is 0. Okay? That's this edge, and this is where x24 is 0. This is where x25 is 0, x35 is 0, and x13 is 0. Okay, you see what's non-trivial is that the corners then are the pairs of poles that are consistent together, right? So here I have both x13 and x14 go to 0, and so I get a double pole here, and so on. Okay, so this picture sort of captures the pattern of how the poles can come together. And it's not obvious a priori that you should be able to capture the pattern of the combinatorics of the poles that come together by a shape like this, but it ends up being true. Now let's do another example. So we can draw this another way, that we have we're associating every partial and full triangulation, all the partial triangulations of the pentagon with the facets of this shape. So if this is my pentagon, not the same pentagon, this is my underlying pentagon, then this could be the edge 1, 4. This could be the edge 2, 4, and this vertex will be the complete triangulation. 1, 4, 2, 4, right? So what I've managed to do is decorate all the edges and all the vertices of this pentagon with the partial triangulations and complete triangulations of the 5-gon and the underlying 5-gon in such a way that well, in the way that all the obvious compatibilities are satisfied. So, okay. Now, this example is also not super convincing. There's something interesting going on, but of course it ends up being true in general. That's what the Associahedron is. Okay? So the Associahedron for n particle scattering is an n-3 dimensional polytope. Okay, and the combinatorics is that every face of a polytope is a partial triangulation. You can think of it as a collection of chords, C. Okay, and that is a face. I mean, one face is a face of another face, or belongs to the face of f prime if this partial triangulation C is a refinement of C prime, or if you think about giving this partial triangulation just as a list of chords, if C prime, if just as literally a subset of C. just the set of chords that occur is just a subset. Okay? All right, so that's the sort of combinatorial. Well, that's the claim, is that a polytope exists with this property. Okay? This is not trivially obvious to begin with, but can I switch now, Mateo?
Yeah.
I'll show some pictures.
Sure.
Okay.
I think it's sharing online, but I'm not sure. It's just.
So this is, I'm sure, a picture many of you have seen. Let's stare at the. Where did? Okay, here we go. All right. Okay, so that's what this is what the three-dimensional association looks like for n equals 6. So you see, it's this much more fancy-looking three-dimensional shape, but as advertised, every single face of this guy corresponds to some partial triangulation of the polygon. For example, the facets, the codimension 1 boundaries are just single chords. Okay, and so you see, we have two kinds of facets. We have these square facets here, which correspond to one of these long diagonals. And we have these 6 facets that look like pentagons, okay? Look like these pentagons that correspond to these short diagonals. And as you've seen, all the remainder of the edges and the vertices are decorated with partial triangulations and full triangulations. Okay, so this guy, this edge, is this and that, which are precisely the chords associated with the faces that touch it, and so on. So when I get to the vertices, they correspond to complete triangulations. So this is kind of a remarkable fact, that just the pattern of how the poles come together is captured by this shape. Okay, that's not obvious a priori that had to be the case. So our second experimentalist, and by the way, our second experimentalist might not be as smart as Jim Stashev to produce this object. Okay? But in fact, there's a way that you could even see that something like this is possible. And this is, incidentally, a second practical method for seeing whether you're dealing with the geometry. So I'm about to tell you in this practical setting. So let's say you're an experimentalist who got excited about the fact that your pentagon worked. Oh, by the way, what does n equals 4 look like? N equals 4 is really boring. N equals 4 just looks like this. It's just an interval where on one end you have this triangulation, on the other end you have that triangulation. Okay, so n equals 4 is pretty boring. So your experimentalists have seen n equals 4 and n equals 5 are captured nicely by shapes. But what about n equals 6? Okay, you have to be, how would you come up with a shape like this? Well, you might not know that it can be a shape, but you can do the following. Just always do what you can. You can count how many, if there was a shape, you know how many faces it would have to have. You just count how many single one guys. So the number of faces is equal to the number of these single chords is equal to 9. And then you just count the number of edges. You just count, you just count however many of them there are. So if the object exists, its number of edges would have to be 21. You just count them, okay? And you count the total number of complete triangulations, which would be the vertices of the shape, that is 14, okay? And you just count those. And if the shape existed, you say, okay, that's what its number of faces, edges, and vertices would have to be. And so how can you check whether there's a hope in hell that this is a nice shape? You compute the Euler sum, right? The Euler sum is 2. So it has a chance. Okay? It has a chance, and boom, there it is. Okay? Now, this is also something which has served us well over and over again. A kind of a much fancier version of this object and this kind of game went on with the discovery of the Associahedra It took us 2 years to discover the amplituhedron, even though we were sure it existed, but it took 2 years. And the thing that kept us going for all that 2 years was Lauren's work from her thesis that explained how you could check whether these interesting Grassmannian objects were balls by doing Eulerian sums of counts of how many vertices, facets, blah, 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 they could have. So even though we had no idea what the hell the object was, we had a lot of data. We computed residues of our fucking objects, and we checked that all of these numbers of order hundreds of thousands were canceling to give you others or the numbers of zero the whole time. They're all balls, okay? This was such a massive miracle that it could not be an accident, and it was the main thing that kept us going for a long time. So this is another thing that you can do. So I'm just, these are not, there's no surefire method, but you check if you have the log forms. You check whether when you compute residues of these guys, it even makes sense to try to associate the singularities with faces of something. And the checks have these very basic sort of topological characters to them. But when they work, they're so miraculous that, that it's very unlikely to be an accident. Similarly here, you can actually go do this exercise. If you've never heard of the Associahedron, you can do this very simple exercise of making a generating function that counts how many partial triangulations there are. It just extends the exercise that many of you know for how it counts all the diagrams, which is the recursion relation for the Catalan numbers. It's a very similar exercise. It just gives you all of the face numbers, all the partial triangulations. And there is a remarkable fact that if you take the alternating sum, the sum is always zero. Okay, so that is but that shows there is something non-trivial going on. It's not super obvious ahead of time that they should be captured by a shape like this. Okay, so our hero experimentalist gives this clue in their imaginary talk, in their imaginary world, and this. And interesting, see, the first clue about factorization is in every textbook. The second clue that the pattern of poles is polytopal is not in every textbook. And this is something that we've really only started appreciating recently. But the amazing thing is that this knows more about the amplitude than the first clue does, because this actually knows also about factorization. How does this know about factorization? What does factorization mean? Factorization involves what happens when you put a single chord to zero. So that's like going to the faces of this object, right? Well, there's two kinds of faces. There's the square faces and there's the pentagonal faces, right? But you see that what these faces look like are not random. These faces are the product of lower Associahedra. Okay, so for example, if you go to this face, it looks like a pentagon, and the pentagon is the product of the Associahedron for this 5-point guy, which is the pentagon that we talked about back here, and the association for the 3-point, which is nothing, doesn't have any propagator, so in that case, it's just the point. Okay, so the Associahedron factors onto itself, and this guy, meanwhile, is the product of the Associahedron for this 4-point, which is an interval, times the Associahedron for the other point, which is interval. Interval times interval is a square. Okay, that's the remarkable feature of the Associahedron. You go to the facets, and the facets are not random. They're products of lower Associahedra, right? So the fact that the pole structure is polytopal is unobvious, but it definitely also knows about factorization, whereas just saying the word factorization definitely doesn't know this. So somehow this is more, this is better than just standard factorization. All right. Okay, so we're going to talk about, now we're going to talk momentarily about where this comes from. But since we're also talking about cosmology, let me tell you what the analogous object looks like in cosmology. Looks like that. Okay, so this is the Cosmohedra for the case of for 6 points. And let me tell you what this object is. So what is this object combinatorially? So just like the Associahedron, is we have facets associated with collections of non-overlapping chords. And we say that F is a face of F prime if C prime is a subset of C. So the cosmohedron is exactly the same on the nose with the word subpolygon, with the word chord replaced by subpolygon. Now, you see how it works. You get a picture. So cosmohedron is an object whose faces are associated with collections of non-overlapping subpolygons. Again, non-overlapping means they can't cross. They can be disjoint. One can be contained inside the other, but the edges of the subpolygons can't cross. There's one little stipulation that we call the Russian doll rule, which is very simply that. So when I say collection, I literally mean a list. You give a list of subpolygons: P1, P2, P3, P4, and it just has to have the property that any two of them don't cross. They can be contained. They can be destroyed. They don't cross. The only stipulation is that if a subpolygon has other subpolygons inside it, it must be fully covered by subpolygons. So if you have some subpolygon and you have another little polygon inside it, it must have the complementary part as well. Okay, so that's it. So that's what we call the sort of the full Russian doll rule. But with that stipulation, this is the definition for what the faces are. Okay, and then the rule is exactly the same. That F is a face of F prime if this collection P prime is a proper subset of P. Yes.
Just looking at the combinatorics of the second polytope.
Yes.
At first, I thought you got it from the associahedron by truncating it all the vertices and edges.
Yes.
But then I see that the result is actually not simple.
It's not simple. That's right.
Yeah.
Exactly. So this is a really key point. I'm going to come to this in a moment. It is not a simple polytope. You could make the simple object. So I could make well, let me just say to you. So we have these non-simple things all over the place. You could make it simple. That's what we call the permutahedral blowup of the associahedron. That's also a nice object, but it's not as nice as this one. It's not the one that captures the physics. Okay, and so but if you just look at this picture, well, okay. So I've labeled here every one. But there's a close relationship between these two objects. You see, every vertex of the associahedron, every face of the associahedron of every dimensionality has turned into one of the facets of the cosmohedron. Okay, and now all the vertices of the cosmohedron are all the Russian dolls that show up in the waveform. Okay? Every term and all the Russian dolls that show up in the waveform. For that, we see. Let's see. This is this. Sorry, apologize. It's a little. Sorry. There. Okay. So here's a little blow up of one of these regions. And so you see that we can think of every single one. So here I can equivalently think of all of these guys as for example, I thought of this face as just being associated with this chord. I can equivalently think about it as this collection of non-overlapping subpolygons. Okay, so every facet is a simple collection of non-overlapping polygons. That's just exactly what I get from a collection of chords. But then when facets meet, it's compatible subpolygons filling each other. So that by the time we get down to the vertices are precisely a complete collection of non-overlapping subpolygons that give me the contributions to the wave function. Okay. Okay, so this is telling you what the object looks like. There's actually here's maybe a simpler example. if we go back to the pentagon, okay, that's what the icosahedron looks like. And you see, to get these the cosmohedron, we've sort of shaved off every vertex of this 5D icosahedron. Everyone has been blown up. So again, every facet of the cosmohedron is one of the edges or vertices here. Okay, so this guy, so this vertex is now this edge. This edge is this edge here. But you see that vertex, so now I can equivalently think about this edge as this set of nested of non-overlapping subpolygons. This guy is a set of non-overlapping subpolygons, and that vertex is putting them on top of each other, which is this Russian doll. Okay. All right. Yes.
Is there a version of this labeling where you're looking at the combinatorics, the tubings instead of the polygons?
Yes, in fact, so there's a story for every graph by itself, which is the graph associahedron, which is the combinatorics of the region. Okay? But I'm just sort of just jumping to the end, just so you see what the full object looks like in the end, because the sort of remarkable thing is, independent of how we get it, just how amazing the parallel is. Okay, it's literally on the nose the same. You just replace the word non-overlapping chord with non-overlapping sub-polygons. And now I'm going to tell you how to think about this object in the 15 minutes I have left. Any questions? Yes.
Polygon should have a particular non-overlapping subpolygons in
Yes.
this dimension.
Any dimension. Any dimension. Anything you want. So long as they're not non-overlapping, everything is fine. Everything is fine. Okay. Okay. So, but I hope it's obvious why we're happy about this. Because exactly what we hoped for, which is that, the amplitude should live inside the wave function. There should be some kind of geometry for the wave function. So that suggests that there should be some way that the wave function, the amplitude are related to each other. And there it is. Right? It exists in the Platonic world of mathematical ideas. This thing exists, and it does exactly on the nose what it's supposed to do. Similar objects were encountered by mathematicians, by Kapranov in the 90s, had something roughly with a flavor like this. Posnikov and friends in the past sort of 4 or 5 years have had objects with this flavor, but not literally this guy. And this is the sort of thing that you look for if you're a physicist, because it has to exist. And of course, so it's very nice that it does. All right. So yes. Yes.
So for the geometric construction of the polytope.
Yes. I'm now going to tell you how to construct it. Yes. Yeah. I'm just showing you what the combinatorics looks like. Now I'm going to tell you how to actually construct it. Okay. Okay. So maybe that's it. Can I go back, Matteo? Okay, so I'm now going to give you a lightning introduction to the way we had of thinking about the Associahedron. By now, there's many ways of thinking about the Associahedron. Of course, the Associahedron is an ancient object that's been understood in lots and lots of different ways. Our way overlaps with a number of these old ways. But there's a sort of more uniform way of thinking about it that extends beyond the tree-level scattering amplitudes that I was talking about to all loop order. And as you'll see, the story of the Cosmohedron also is just piggybacks off the Associahedron. So it just generalizes to all loop order in exactly the same way. Okay, so, but I'm not going to give a full-throated introduction to the various ways of thinking about the Associahedron. I'm just going to tell you one of the ways, one of the equivalent simple ways we've had to think about it. But just to give you a picture, And here, sort of positivity is gonna play a very, very big role. So if we go back to 4 points. Okay, our kinematical variables are like x13 and x24. So I'm gonna tell you there's an associahedron in kinematic space. Okay, so that means in the space of x13 and x24, I'm gonna find an associahedron. For 4 points, the associahedron is just an interval. So this is not gonna be too exciting associahedron, but still, we're gonna see a little interval in this space. But the space is two-dimensional, right? The associahedron is one-dimensional. In general, the space is nn minus 3 over 2-dimensional, roughly n squared dimensional. Whereas the number of variables is roughly n squared variables, but the space is roughly n dimensional. Okay, so it's n minus 3 dimensional. So we have, obviously we have to do something. We have to be restricting to some lower dimensional plane in the big space of kinematic invariance in order to see the associated. Right, but let's just see how this works already in this very simple example. All right, so I have x13 and x24. x13 and x24. Now, how am I going to get something one-dimensional out of this space? Well, I have to somehow see something one-dimensional here. So, but I don't want to break the symmetry between 1, 3 and 2, 4. Right? So here's what I'm going to do. I'm just going to decide that I'm looking at a plane, just a line in this case in this space. I'm looking at a line where x13 plus x24 is equal to a constant. I'm going to call that constant C13 for reasons that you'll see in a second. Okay. Now, on top of that, it's reasonable to look, I'm sorry, maybe before saying that, it's clearly reasonable to look at the region where x13 and x14 are both positive. Why? Because we know that we somehow want the amplitude to have poles when the x's go to 0. Right? So if the amplitude is going to be the canonical form of something, then it should have poles, right? It should have poles, and the poles should occur when the x's go to 0. Okay, so I want to have this is so I somehow want to begin with this positive orthant, but I want to get to a one-dimensional space out of this, right? So I'm going to do that just by restricting my attention to x13 plus x24 equals C13, where C is also positive. Okay. So if I do that, then this is my space. Okay. And if I look at a one form on the big space, so I'm going to write the following one form on the big space. Omega is d log of x13 minus d log of x24. The minus sign is going to end up being there for a very similar reason as in our discussion earlier. Okay, but then if I look at this form and I pull it back to this one-dimensional space, what do I get? I mean, this is dx13 over x13 minus dx24 over x24. But pulled back to the space, this is going to be, let's say, solve for x24. This is going to be dx13 times 1 over x13 plus 1 over c13 minus x13. This is dx13, 1 over x13 plus 1 over x24. Of course, x24 is implicitly defined on that space. Okay? And this is the amplitude. And in fact, this is the canonical form of that interval on that space. So what I've done is in kinematic space, I found an associahedron. You just go to this part of kinematic space where you freeze x13 plus x24 to be this positive constant. And then, okay, you look at the region on that space where this intersects the positive orthant, and you get a shape. The shape is an interval. The canonical form of that shape is the amplitude. Okay. So this is an example of the question in kinematic space whose answer is the amplitude. Of course, it's a slightly funny question, but I hope it's obvious that nowhere in this question did I say add up all the finding diagrams, right? Clearly, I said nothing like that. Now, in general, this is the story. So I don't have time to explain where it comes from. It's quite natural, even when you see it presented in this way, but it's sort of inevitable for many different starting points that I don't have time to describe in detail because I want to get to the cosmological place. Okay, but here's a story in general. First, we want to think about the kinematic space nicely. So, yes.
When you say the amplitude,
Yes.
like, do you say the amplitude up to tree level?
This is just the tree level. This is just a tree level. The story is an extension to all loop orders, but and also beyond the planar limit, the entire theory. Okay, but I don't have time. Yes, but okay. So we want to just think about the kinematic space, and so the kinematic space is just a space of all the x's. But I really want to be specific about what the x's are. So I'm gonna record the x's in this way. Just let me give you an example at n equals 6. So I'm just gonna make a little mesh like this. I mean, this is the most obvious way that you'd record x's. So here's x13, x14, x15, x24, x25, x26. I mean, it's just a grid. The only maybe slightly funny thing is that I've rotated the grid 45 degrees. That's for fun. Okay. Otherwise, I could have also just drawn it like this, and you would not have complained, right? So 1, 3, 1, 4, 1, 5, 2, 4, 2, 5, 2, 6, and so on. So the most obvious way of drawing it on a grid. The thing is that the problem has a cyclic symmetry. Okay, and so there is something amusing in this picture that if you continue, I mean, I can continue infinitely in all the directions. Okay, but you see here, there's a 1, 3. Up here, there'd naturally be a 3, 1, okay? And then a 3, 2 here. Okay? I've drawn it in this 45-degree way because this 1, 2, 2, 3, 3, 4, these are the kind of edges of the polygon that we don't think of as variables, right? They're just the on-shell things on the outside. So so it's sort of more natural to have them as vertical lines. If I drew it the other way, that'd be 45-degree lines. Okay, but so I'm just drawing it like I'm drawing it like this. So it's interesting that the problem has it doesn't while the whole thing is cyclic, the picture is cyclic only by 2 because there's like a Mobius symmetry here. I go from ij to ji back to ij. Okay, so it has periodicity that's twice what you would naively expect. But anyway, if I draw this picture, then I want to just choose some chunk of this mesh that contains all the variables once and only once. Okay, and there's many ways of doing it, but this is one nice way of doing it. Just this little triangle. Okay, just this little triangle. And you see here, all the x's occur once and only once. There's 1, 3, but not 3, 1. 3, 1 is outside there. Okay, there's 2, 4, and not 4, 2, which is out there somewhere, and so on. Okay, so in this triangle, all the variables occur once and only once. Now, it's a little bit amusing if you're a physicist, maybe not if you're a mathematician, but if you're a physicist, if you see any picture like this, you think about light cones in Minkowski space. Okay, so you would naturally sort of think, and this is nothing to do with space-time, but you would sort of think of this as sort of a time direction, and this is a space direction. And then there's a natural notion of like whether 2 points can causally affect each other or not. You know, so if 2 points are close enough, they can causally affect each other. But if one point is like here and the other point is there, they can't causally affect each other. Or if they're too far apart, they can't causally affect each other either. Okay? Well, there is something a little bit remarkable in this picture, that this notion of quote unquote time and quote unquote space in this purely kinematic space actually has a meaning. Because remember, things matter a lot. Things matter a lot, whether chords intersect or not. And so you see, when chords intersect, see, let's say I have 1, 4, and 3, 6 intersect. Okay, 1, 4, and 3, 6 intersecting Well, look at that. Here's 1, 4. Here's 3, 6. And they intersect because there is a causal diamond. There's a diamond that has 3, 6 as the future and 1, 4 in the past that fits inside the space. Okay? So if two chords intersect, there are the past and future corners of a causal diamond that lives inside this funny kinematic spacetime. On the other hand, 1, 3 and 1, 4 don't intersect. 1, 3 and 1, 4 are perfectly compatible, and that's fine. That's not true of 1, 3 and 1, 4. They're not the past and future. They're not the past and future corners of a causal diamond. Neither 1, 3 nor 4, 6, right? 1, 3 or 4, 6. 1, 3 is sure down here. 4, 6 is sure up there, but there just isn't room for their future light cones to intersect each other. Okay, so it's kind of fascinating that simply recording the position, simply recording the kinematic variables, brings to life this little notion of quote unquote causality in this kinematic space that has something to do with this crucial issue of compatibility, whether chords cross or not. Okay, so that invites us to think of some kind of dynamics in this kinematic space. And that's what we're after. Remember, what we're trying to do is find a question in this space whose answer is going to give us the Associahedra, right? And then the canonical form of that Associahedra is going to be the amplitude. So that's what we're trying to do. But we don't want to borrow the Associahedron from Sashef and others. We want to somehow discover it in this space. All right. But we've taken a clue now that there's some kind of natural causal structure in this kinematic space. And so now what we're going to do is our dynamics in the kinematic space is going to be the one-dimensional wave equation. All right. Now, what is the one-dimensional wave equation? It's du dv x equals 0 in the continuum. This is discrete. So what is du dv? Du dv is this plus this minus that minus that. Okay. So that's the equation we're going to write down. We're going to write down the equation xij plus xi plus 1 j plus 1 minus xi j plus 1 minus xi plus 1j equals some right-hand side that we call Cij. Okay. So we're going to write that down, and we're going to imagine theCijs are fixed. These are like sources of the wave equation, right? That we're going to imagine theseCijs are fixed and positive. And we're going to ask for all the Xijs to be positive. That's it. The claim is if you put that on the computer, you'll get the Associahedra. Just plot it on the computer, you'll get the Associahedra. Okay? That defines the Associahedra. Just a clue. Why does it define the Associahedra? And remember, the Associahedra does many things. There's a vertex for every triangulation, blah, blah, blah. But in particular, what the Associahedra does is it makes sure that chords that cross do not occur together, right? Remember, every chord is going to correspond to a face of the Associahedron. So the zeroth order thing is that chords that cross should not be able to meet, right? That means that I should not be able to put two crossing chords to 0. Why can't I do that? Well, this equation is just the little equation that looks like x plus x minus x equals c. Okay? Something that you're used to from high school physics is Gauss's law, is the sort of integral form of these equations. The general form of these equations is that if you have any diamond whatsoever, the past plus future minus left minus right, past plus future minus left minus right is equal to the sum of all the c's on the inside. That's the sort of integral form of Gauss's law. We can just get it by adding these equations. If I add this equation to this guy, that guy, that guy, that guy, all these intermediate things cancel out telescopically, and I'm just left with this plus this minus that minus that. Okay, so this is the integral form of the Gauss's law. And since all the c's are positive, this is also positive. And now comes the lovely thing about positivity. Okay? What we're trying to say is that for any diamond like this, it is impossible to set both the x for the past and the x in the future to 0. That should not be part of the space. That would correspond to two crossing chords. And Why is that impossible? Well, it's obvious. If I put p to 0 and f to 0, this is a contradiction. I have the sum of two negative numbers equals something positive. So that's why that gives you a zeroth order idea of why this is cutting out the association. In fact, you can go further and it's literally a 5-minute exercise, but I want to use my 10 minutes for something else. You can just show from these equations that when you go on any x equals 0, the object you get is the product of two lower associahedra. Okay, that's just a direct consequence of these equations, just trivially. So this picture makes it obvious that the pole structure is polytopal. It makes it obvious that the object factorizes into products of lower things on its own. Okay. A final thing this picture makes obvious, and I'll just mention this because it's one of the best open problems about the cosmological avatars of these guys. So let me draw what this looks like for 5 points, because it's so simple for 5 points to work it out. Okay, so for 5 points, just to do it explicitly, so I have 1, 3, 1, 4, 5, 2, 5. So so I'm supposed to have x 1, 3, 1, 4, 2, 4, 2, 5, and 3, 5 are all positive, but so that's my 5-dimensional space, but it's restricted down to 2 dimensions by these equations. 1, 3 plus 2, 4 minus x 1, 4 is this. There's a little c 1, 3. And then this one. Okay, so I have x 2, 5 plus x 1, 4 minus x 2, 4. By the way, these x's on the outside are 0. Okay, they're not, they're set to 0, they're not part of our so we're putting all those boundary x's to 0. This is equal to c1, 4. And finally we have x 2, 4 plus x 2, 5 minus x 2, 5 equals c2, 4. And so these, okay, so I'm restricted to these, but I have to have that all of them are positive. And so I can just solve, so it's sort of natural in this picture to imagine that sort of this is the past in my kinematic space-time. I'm going to solve for all the other ones in terms of 1, 3 and 1, 4 and everyone else. So it's just trivial to solve these equations to get, for example, that x2, 4 is c1, 3 plus x1, 4 minus x1, 3. And x2, 5 is minus x1, 3 plus c1, 3 plus c1, 4. And x3, 5 is minus x1, 4 plus c1, 4 plus c2, 4. Okay, so so now I just have to ask that all the x's are positive. So let's see what it looks like. It's a now 2-dimensional space parameterized by x1, 3 and x2, 4. Okay, so here's x1, 3. Here's x2, 4. Sorry, x1, 4. So they both have to be positive. But now you see that I have to have that x2, 5 is positive. That says that x1, 3 can't get bigger than c1, 3 plus c1, 4. So x1, 3 is less than something here that is c1, 3 plus c1, 4. Similarly, x1, 4 is less than something up here, which is c1, 4 plus c2, 4. And finally, x2, 5 has got to be positive. So x2, 4 has got to be positive. These are all positive. Okay. So this line here, this line here is when x2, 5 goes to 0. And of course, this line here is when x1, 4 goes to 0. When x1, 3 goes to 0. These are corners. Okay. But finally, this equation for x2, 4 says x1, 4 minus x1, 3 is bigger than negative c1, 3, and that's a line like this. Okay, so this is x2, 4 goes to 0. So the associahedron is the inside of this pentagon. Exactly, we knew that it had to be a pentagon, and there is the pentagon coming out of this example. Okay. Okay. Now you'll see how important the positivity of the C's are. Because for this shape to be correct, it was important that this 45-degree line was on this side of the two things that cut out the rectangle and not on the other side. And that was made possible by the fact that this is C13 plus C14, whereas this intersection point is just C13. Because all the C's are positive, this is always to the right of that, and similarly on the other side, okay? So the positivity of the C's is absolutely crucial for this picture to make sense. But something else that this picture makes obvious is that not only that we have an associahedron, but that it's naturally built from simple pieces. And this is also something which is made very obvious from this sort of from the wave equation analog. How do you solve any wave equation if you're a physicist? Use the Green's function method, right? To solve the wave equation with some set of sources, you first solve what it looks like for delta function sources, and then you add up all the solutions because the equations are linear. What are the sources in this case? They're the small meshes. So in order to get the full answer, it's useful to first see what happens when you shut off all the meshes but one, then you get some shape, but then you should add the solutions together. Well, adding in this case means adding the polytopes together. That's the notion of Minkowski's sum. So from here we learn that the associahedron is actually a Minkowski sum. That's something else that kind of is made obvious by this picture. It's a Minkowski sum that looks like C13 times whatever the associahedron looks like when only C13 is equal to 1 and the others are 0, plus C14 times the same thing, plus C24 times the same thing. And this guy, well, we can just see from this picture what it looks like. If I set the other two C's to 0 and just C13 to be non-zero, this guy's an interval that looks like this. This guy's an interval that looks like this. This guy is a triangle that looks like that. Okay. So that's a really, yes.
So you're technically a bit over time, so it might be good to kind of take a pause or
Sure,
maybe
yes.
switch to informal discussion.
Sure, yes. Why don't we just clap?